Hey, it's Tony from Adafruit, and in this video it's the third part in the Circuit Walker Sneakers project, which is a project to make sneakers that light up based on the accelerometer in Circuit Playground. So it detects when you take a step and it does some cool little animations like you see right here. So this is a version that's using the Circuit Playground Express board, and this is actually using CircuitPython. So I've done two previous videos. The first two are using an Arduino version of this project that works with Circuit Playground Classic or Express. And I went through how I adapted a step detection algorithm that uses accelerometer data to figure out if you've taken a step, like you've lifted or you've put your foot down on the ground, and then it just lights up pixels to animate them. And actually, this is the Arduino version right here. So in the very first video, I did a simple version, and then in the second video, I did a more advanced version that uses this adaptive step detection that's actually pretty good at detecting steps. So in this one, you can tell if I do like a really light step, it detects that. But if I do a heavy step, it also detects that. So really cool algorithm that works well. But I've gone in this video, in the third video, I've ported this algorithm over, well, not really ported the algorithm, but I've built the same basic project using a board that can run CircuitPython. So that's a version of MicroPython that lets you run Python code on a little board like Circuit Playground Express. This board's purple because it's a prototype board, but if you get a Circuit Playground Express, it's probably a black board that you would have. And anyway, so let's look in this video. First, I'll show how to load this code and actually just use the Circuit Walker sneakers that are Python powered. And then I'll walk through the code and kind of explain how it works and show how I adapted the idea of the Circuit Walker sneakers to run under some of the limitations of CircuitPython and MicroPython, because it's much more expressive as far as what code you can write, but it's not as performant, which is to be expected because it's Python code that's being interpreted. But you don't really need a lot of performance, it turns out, to get a cool effect like this. So you can see, you know, when I move this shoe, I have to kind of kick it with a little more force than the Arduino version, so it's not adaptive. So you can see if I'm doing a real light step, it doesn't pick that up. But if I take a big enough step, then it picks it up and it does a little rainbow cycle animation on here. So like I said, I'll start with how to load this. So if you just care about making this project work, stick around for the first half of this video, and then I'll explain how the code works in the second half, which is a really good way if you're still learning CircuitPython or MicroPython, good way to compare an Arduino version of a project to a CircuitPython version and kind of see what's maybe what works well in one version, what doesn't work as well in the other, what are some of the compromises you have, and just what are the syntax differences and how the code works like that. So we'll dive in and get started here. I'll jump into the main view. Let's see. Yeah, we'll do that. Like I said, so in the upper right-hand corner, I have a couple versions here. So this is the Arduino version. This is running on a Circuit Playground Classic, but it doesn't really matter. The Arduino one works on both the Express and the Classic. And I'll put a link in the description when this goes on YouTube. So look below, you'll see a link to the first two videos in this series. So if you're interested in that adaptive algorithm on Arduino, definitely check out those videos. And then this is the version that's running CircuitPython code. It's kind of nice, and it looks similar. So if I tap this, if I get that one animating, you know, they both have the same animation. It's a rainbow that kind of circles around. But like I said, the algorithm's a little bit different on the Python one, and we'll look at that. So like I said, we'll start with how to start from scratch. So you've got your Circuit Playground Express board. And like I said, this only works with Circuit Playground Express. And I'll put a link in the description below so you can go directly to the product page to check it out. Circuit Playground Express, it's our all-in-one electronics learning board. It kind of looks like this. And I've done a bunch of videos on this. It basically takes the brains of what was an Arduino and puts it into this tiny little circular board, and then you have a bunch of inputs and outputs around the side. There are NeoPixels that are built into it. There are 10 of them. There's a circle of them. And then there's also an accelerometer in the center, along with a few other sensors and things. But that accelerometer is what we're going to use to detect steps, or at least detect a strong spike of force that we can then use to light up the NeoPixels on the board. So to start with, you'll need to get CircuitPython running on your Circuit Playground Express. And for this project, I've written it so it works with the Circuit Playground Express board. So that's the one that has everything built into it. You could build a version of this with a standalone, like a Feather M0 potentially, and maybe a strip of NeoPixels. Maybe I'll point out in the code where you might need to change some things. You'd also have to add an accelerometer, the LIS3DH, which we have a nice little breakout for. So you could build this with a bunch of smaller components and maybe have like a strip of NeoPixels that you put around your shoes or something like that. Totally possible, but this project is really meant to just show how easy it is with Circuit Playground, where you don't have to do any soldering. You just pick up the board. Everything's attached to the board already. You don't have to connect anything or wire anything up. I've literally just zip tied this to the laces of my shoes right here through a few of the holes on the outside. And then this is a battery that's behind here, a lithium ion battery that I have. But you could also use like a AA battery pack. This is one that we have in the shop. So however you can power this, it should work. But anyway, start with your Circuit Playground Express, and the first thing you need to do, right now Circuit Playground Express doesn't ship with CircuitPython on it. Maybe in the near future it will. If you get like the Gemma M0, it does ship with CircuitPython. But you need to get CircuitPython firmware running on the board, because that's the interpreter that lets you run Python code. So unlike with Arduino code, you write your code in the editor and you press upload, and that will just upload all of your code, including all the libraries and things that Arduino needs, onto your board. With CircuitPython and MicroPython, it's a little bit different in that you first need to load onto your board the Python interpreter, which is actually the magic that knows how to take your Python code and interact with everything and run that code on the board. And then once you've loaded the Python interpreter, now your board can run Python code, and you can actually copy over Python source code just as a .py file, just as if you would write Python code on your computer. You can copy that code onto your board, and for this board, the Circuit Playground Express, it shows up as a USB drive if you plug it into your computer. So you plug it into your computer, you should see a new drive pop up, and then you can copy your code onto the board. So it's a really nice, easy workflow that I'll show how to do in this video. So, like I said, to start with, I'm going to plug in this board, and I'll show real quickly how to load Oops, this thing's running the demo sketch on it. So, oops, let me turn off the sound effects. There we go. So out of the box, you'll get something that, it's probably running a little demo like this one is, but I need to load CircuitPython, and the way to do that is you go to the CircuitPython repository. This is kind of the main homepage of CircuitPython. It has links to all the documentation and things inside of it. But to load it onto your board, on your Circuit Playground Express specifically, go to the Releases tab up here. And then from the Releases tab, find the latest release. So like the 1.0 release is the latest one for here. And scroll down and you'll see all of these files that are associated with this release. These are the firmwares for different boards. So you need to pick the firmware for the board that you're using. And in our case, we want this top one right here, the Circuit Playground Express 1.0 .uf2. So this is important, that .uf2 extension. You might see on older releases, at least, there are also .bin, .binary versions of the firmware. That's for if you're using a special tool, this BossSC tool, to upload. But for our board right here, we actually don't need to do that. Like I said, it can show up as a USB drive. So you want to download this .uf2 version of the Circuit Playground Express firmware. So this file right here. So download that to your computer, and I've actually done that ahead of time. So let me go to my downloads here. And what I did was I downloaded it. If you're on Mac OS X, you might need to rename it. So you can see it's a really long file name right here. Sometimes we've noticed with some versions of Mac, and depending on the version of the bootloader that you got on your board, you might need to rename it to a small file name. So I just called this cexpress1.uf2. Same exact file, I've just changed the file name. But what I'm going to do is I'm going to double press the reset button. So like you're double clicking the mouse, there's a reset button in the middle of the board. I'm just going to press it twice really quickly, and we'll see, oops, oh, it reset itself. So let me see if I can get it to go into the firmware. Oh boy, interesting. Wow, so maybe this one's not loading up. I might not have the right version of the bootloader on here. Oh boy, this is maybe not the best demo in the world for this. Interesting why it's not going into the bootloader for this. Let me try this one more time. Huh, interesting. All right, well, this board's being a little bit interesting. I'll have to look at this board later. I'll fall back to showing how to do it on this board right here. So this is my main CircuitPython board. Like I said, this is a prototype board, but it behaves just like the other boards. So you double press the reset button, and you should see something like this, where the board turns green like that. You see all the LEDs light up green, and that's basically telling you it's ready to have firmware loaded onto it. And you'll actually see this CPlay boot drive show up. So I have a drive that shows up for this, and you'll see files like this current.uf2 file on here. But what I want to do is drag that .uf2 file that I downloaded from my computer onto this CPlay boot drive. So if I go into my downloads again, and if I grab that UF2 file, and again, I renamed this to make it shorter because sometimes on Mac OS X, if you get an error that says it's out of space, you need to rename it to a short file name, like less than 8 characters long right now, just a workaround for an interesting little bootloader issue. But I'll drag that over, and it just flashed the firmware on here, and it happened really quickly. But you might have noticed like one of the red LED on the board kind of flashes for a moment as it's copying over the firmware. But now this is running CircuitPython. And because I actually already had some code running on this board, it's actually running this sketch already, but it's probably not going to do anything as soon as you load the firmware onto it. But then at this point, you can open up the serial REPL, or the read, evaluate, print loop, and that's how you get the Python prompt with CircuitPython and MicroPython. So that's how you can just go and interactively type in Python code. And there are a lot of ways to access this. I've done a guide on how to access the serial REPL. On Mac, I'm going to use the screen command to do it. On Windows, you can use PuTTY, is a nice little GUI tool to access the REPL. But basically, this board will show up both. It still shows up as a USB drive. So if I go back to Finder, it's now called CircuitPy is the name of this board, or the name of the drive. And this actually has some Python code that I've already copied onto the board's little flash chip. But you can see your code here, but it also shows up as a USB serial device, or as a serial port on your computer. So I'm going to access that serial port from my Mac. And from your Mac, if you're curious, you can list all your serial ports. If you list everything under the tty.star path like this, this is going to show devices. So there's like a Bluetooth serial port, which I think you get by default on Macs. And then this USB modem 1411. So this is the serial port for this Circuit Playground board that's connected to my computer that's running CircuitPython. So I'm going to use the screen tool to connect to that serial port. I have to tell it the name of the port, so that USB modem 1411, and then I have to give it the baud rate, 115200 baud. That's just the fixed baud rate. It's always going to be that for CircuitPython and MicroPython. So I run this, and I probably don't see anything, but if I press enter, well, I don't actually see anything either, but normally if you press enter, you'll see a Python prompt if there's no other code running. But because I actually have some Python code that's already running on here, it's the sneaker code itself, I need to stop it. So I can press Control-C. So Control-C, and that stops everything from running. And now I actually see I'm at my Python prompt here. So I can say, hey, hello world, and I get all my Python execution, or my Python code is running. So that's cool. So that just helps confirm that I've got CircuitPython running on here. And it's also important, you can actually see it prints out the name of or the version of CircuitPython. So you do want to make sure you have at least version 1.0 for this to work. So at this point, I've got CircuitPython running on here. Now I need to get the code copied onto this board and running. And it's actually pretty easy to get this going. So there are two things you need to do. Before you copy the code onto this board, I need to copy some dependencies onto here, because this code depends on accessing the accelerometer that's built into Circuit Playground, and also the NeoPixels. And so there's a few different libraries that you need to copy onto the board to make this work. Now, luckily, it's actually getting pretty easy to copy these libraries over to your board. So we have what's called a bundle, which is we've taken all of the libraries that we've created so far for CircuitPython, put them into one download, so you can just download a zip file and just copy that entire download onto your CircuitPython board, and that will copy every library over. And we put enough space onto the flash chip of this board that you can fit all of the libraries on there and still have a lot of room for your code. In the future, who knows, we'll have to see as we get more libraries which ones we include. But definitely for all of the things that are built into Circuit Playground, we want to make it easy so that you just copy one thing over and you're ready to go with that. So to do that, then, it's actually pretty easy. You'll want to go to, from the CircuitPython repository, we mentioned there's a CircuitPython bundle repository, and I think we have a link to it in here, but maybe we don't. So I'll go to it directly from Adafruit's GitHub account. If I search for bundle, then you find this Adafruit CircuitPython bundle. And so this is the repository that you want to go to. And it mentions on here how to load the bundle onto your CircuitPython board. So it's pretty easy. You just want to go to the Releases tab, and then you want to download the zip file for the latest release. So this is the 1.0 Release Candidate 2 release. So I download this file, and then and I'll show you here. So I've downloaded this ahead of time in my Downloads folder here. And so this is the zip file. When you extract this download, you'll find this lib folder. So that's what's inside the zip folder, and there's all kinds of stuff inside of here. This is the bundle. So this has a copy of the binaries of all of the libraries that we've created so far for CircuitPython. So stuff for accessing NeoPixels, stuff for accessing the accelerometer, it's all inside of here. So it's kind of nice in that all you have to do is just take this lib file or folder and just drag it onto your CircuitPython drive and just copy everything over. So I'm going to do that. It actually tells me I already have it on here because, like I said, I've already loaded this code on this. But let's just say, yeah, copy it over and replace everything. So it's copying over all of the libraries. And in a moment here, it should finish. There we go. So I just copied over all the libraries. So that's it. So I have all the dependencies on here, which is kind of nice. You don't have to go and track down neopixel.mpy and the lis3dh library and all that. You certainly can. Those are the two libraries that this depends on. But this is a little bit easier. So copy your bundle over and you're ready to go with this. So that's step one. So that gets the dependencies onto the board. And then the last step is you actually need to get the Circuit Walker Sneaker code onto your boards or onto your board. And so this is from the Circuit Walker repository. This is where I put the Arduino code. So I also put in the CircuitPython version. So there's a new folder in here, the CircuitPython Circuit Walker folder. And inside of here, there's just this main.py. This is the code for this project. It's kind of nice. There aren't a lot of other dependencies beyond this code and the bundle that we just copied over. So all that you need to do is just download this main.py. So you could clone the repository, you could download a zip of the repository, however you get this from GitHub, doesn't really matter. But I want to get this main.py file right here. And let's see, on my machine, well, let's see, let's go ahead and let's download this repository. Just I'll show an example of that. So if I download the zip file, and then if I open this up, that's going to extract it. And if I go to my downloads, so this is the repository. So again, the CircuitPython Circuit Walker folder is what I want. The other ones are for Arduino. Obviously, they say Arduino on them. So inside of there's my main.py. And what I want to do is just copy this main.py onto my CircuitPython drive. So that's the board that's plugged into my computer. Just copy it straight over. Just put it in the root of this drive. So I'll take it and I'll copy it over. And I already have it on this board because I copied it ahead of time, but I'm going to tell it to replace that file. So I copied it, and it should be running now. Well, and I should be careful here. If you've opened up the serial terminal, that serial REPL, then it actually might just still be in this mode where it's waiting for you to type in Python code and it's not running your CircuitPython sketch yet. What you can do, the easiest thing I would say is close, well, you could keep this open. You could press Control-D, D as in dog. That will perform a soft reset. You could press the reset button. That will perform a hard reset, although generally don't press the reset button if the board is plugged into your computer. On Windows in particular, you can run into trouble where if you do a hard reset, Windows might not have written all of your code out to the board. It has some little quirks about small file systems. And so you might get into a state where you actually corrupt the file system. So don't press hard reset if it's plugged into your computer. Eject the drive, unplug it from your computer, and then press the reset button. Or since I have the serial terminal open, you can do the Control-D, Control-D as in dog, do the soft reset. Soft reset is okay to do when it's on your connected to your computer like this. So I'll do that. And it's running, and it just started running that main.py code. So this is now running the Circuit Walker sneaker code. And because it's called main.py, that's actually the code that will run every time this board powers up. So that file's been copied onto the little flash chip that shows up as a drive. So that's saved on my Circuit Playground board, and so it's always going to run that Python code when it starts up. Kind of like in Arduino, when you upload a sketch, it remembers that sketch. Same thing, it's just now it's just raw.python.py code that I have inside of here. And you can see it actually prints out a few things when it starts up, and I'll come back to when I explain how the code works, what this stuff means, but it's just printing out some helpful little values that it computed. But at this point, I'm going to close my serial terminal, and then I'm just going to unplug the board. It's still plugged in with a battery right here. But now it's ready to go. So if it gets a strong enough impulse, you can see when I kick my foot up like this, it will animate, it'll light up. And I was walking around earlier to test this out. It actually works pretty well. It's a pretty simple algorithm as far as it just has a fixed threshold for once the acceleration of moving your foot goes above a certain level, then it considers that a step, and it fires off this little animation here. So if you tap this, you can trigger the animation. Whereas on the Arduino one, it's a little less, it's a little more advanced. And so with this one, if I tap it, sometimes it doesn't get as many false positives. But it's still fine. I think, this still, as you walk around, this animates and lights up, which is still really cool. It still gives you the effect that you want. Now you might need to tune the behavior of this a little bit though, because like I was saying, I can do like a really light step like this and notice it's not firing off. So if I don't take really strong steps, it might not light up. Whereas, here, if I take stronger steps, then it is lighting up. So I'll show you how to adjust some of the behavior of this sketch. And maybe I'll show some of the configuration, and then I'll show, as I show that, I'll explain kind of how the code works. So if you just load this onto your board, then here's how you can modify the sketch. So I'm going to plug it back into my computer, and remember it shows up as a drive. So here's the drive, and here's that main.py. So this is the code that I just copied over, and it's just raw source code. I can use any text editor to edit this file and change that source code. You can also see there's that lib folder that I copied over that has the bundle stuff inside of it. So I'm going to go into my text editor. The Atom text editor is what I like to use, and I'm going to open up, let's just open up the CircuitPython drive right here. So Atom is kind of nice. I can open a folder, and it's going to show me all the files on the left hand side here. And it's actually showing me here is that main.py. I'll just close it. It has 2 copies of it. But here is main.py. So this is the code that I copied over that we downloaded from the Circuit Walker Sneaker repository right here. So this is the CircuitPython code that's powering this little project right here. And there are a few things at the top that you can change. So like in the Arduino versions, I have some configuration here. There is a tap threshold. So this is a value in gravities that you set. So gravity is a unit of acceleration. Basically 1g is the force of like gravity on Earth pushing down on you. So this is basically setting a threshold where if the accelerometer on the board, it has 3 axes. It has an x, y, z axis, so it can detect acceleration in 3 dimensions. If any one of those dimensions sees a sharp spike of acceleration that goes above this threshold, like 1.5g, then it can consider that a step. So this is part of the step detection. So this is how you can tune this. So I set this to a value of 1.5, which means, if I get an acceleration, a spike of acceleration that goes to, a value above 1.5g, or a little bit above the force of gravity pushing down on me, which kind of intuitively makes sense, because if you think of me taking a step, when my foot's on the ground, the accelerometer is just detecting the static force of gravity pushing down, because it's not moving, nothing's happening. Just anything on Earth is just always going to feel 9.8 meters per second squared pushing down on it. But if I move my foot up, I actually have to overcome the force of gravity. I have to give it a force that pushes it above the force of gravity that's pushing it down. And so that's where you see this spike of acceleration. I lift my foot up, and so that's got to apply enough force to overcome 1g. But I'm not applying maybe hundreds of g's. Hopefully you're not stepping with a massive amount of force. It's just a little bit above gravity. So I apply a little bit of force. I lift up my foot, and then I push it back down, and you just repeat that over and over as you take steps. So that's why I set this threshold to a value that's a little bit above 1g, but not too far above, because the higher I set this value, the harder I have to, the more force I have to kick my foot up to set off the step detection. And similarly, the lower I set this value, the less force that I need. to a point where I could set this like below 1, and that it would be kind of a weird value, because then that would just mean when I'm standing still and getting the force of gravity, it's considering that a step. So I don't really want that. I rarely would want to set this below 1. But this is where you could tune this, where if it's not sensitive enough, if you're taking kind of shallow steps and it's not picking them up, try setting it to a lower value, like 1.1 or 1.2, something like that. And I can actually just save that. I'll just press, I pressed Control S, I just saved this file, or I could actually go into the File menu, say File Save. And again, remember, it's saving it onto the drive. So I'd opened up that CircuitPython drive. So I'm just editing this main.py directly from the drive. And you actually just saw a second ago, this thing just flashed, because when it starts up, it usually detects a step because it's just initializing everything, and so you'll see that initial little animation. But I just lowered the threshold, so it should take a little bit less force to set off this animation. So, yeah, I'm noticing that. I'm kind of kicking this up a little more softly than I was before, and it looks like it's setting off the animation. It's a little bit weird because it's still plugged in. I could unplug this, but I don't want to eject. I don't want to unplug it without ejecting the drive right now, so I'll keep it plugged in. But that's one thing you can tune. So if it's not sensitive or if it's too sensitive, you can try adjusting this threshold. And again, you want a value that's a little bit above 1, but maybe not so far above that you have to like stomp or really kick your foot up to set it off. So try tweaking this value if it's not maybe picking up your steps super well. The other value, this tap time limit in seconds. So I'll come back to this in a moment, but basically this is how this algorithm works. Is it's using some features built into the accelerometer on this board. And so that accelerometer has what's called a tap detection, where it can look for these little spikes in the accelerometer axes. And this threshold is one way you set this tap detection. And then the time limit is another little option or knob that you have that you can twist to adjust the tap detection. And so this is basically a window of time that the accelerometer will look at. And you specify it here in seconds. So this is like a quarter of a second. So within a quarter of a second, if it detects a spike of acceleration that goes above the threshold and comes back down below the threshold within that window of time, then it considers that a step or a tap or a click as far as the accelerometer is concerned. So those are the two parameters that control the step detection effectively. You can set the threshold of how far above baseline 1g that the acceleration needs to go, and then the time window or the amount of time that little hump above acceleration has to occur within. And it's pretty particular in that it needs to see that spike of acceleration go up above the threshold, and it has to come back down below the threshold. If it goes above and if it stays above that threshold for more than this time limit of a quarter second, it actually won't fire off the tap detection, because it assumes that there's just some static amount of acceleration. Like maybe you stepped in a car, and someone just accelerated the car, and like suddenly you're moving, you're not walking inside of the car, but your body is definitely in motion and seeing some of these forces. So it's kind of interesting how the tap detection can maybe filter some of that out. But those are the two parameters that control this. And the time limit you probably don't need to adjust. I kind of mentioned here, if you set this down to a low value, then it means that a really fast spike of acceleration has to occur. Like if I change this to, I don't know, let's say 0.1, like, 10 milliseconds. So just, this would happen 100 times a second. If within that little 10 millisecond window, if it sees a spike of acceleration that goes up and down, so a really fast movement, like you really just quickly kick your foot up, then it would fire off if it's set to a low value like that. But if I increase the value, if I go to like, maybe half a second, that just increases the time where it needs to see a spike up and down of acceleration. So that basically means that it would be more sensitive, in the sense that you would probably see it trigger more often the higher you set this value, because you're just increasing that time window so that a spike can occur as long as it goes up and down within that window of time. So the larger the window, just the bigger chance that you're probably going to see a step that causes a spike of acceleration that happens in that window. I noticed a quarter second is about a good time to start with, and you can experiment and tune this up and down and kind of see how it works, and if it changes the behavior here. There's also this step flash seconds. This is the amount of time in seconds that little animation will occur. So you see when it sees a shake here or a tap, it's animating in a rainbow like that. And this is just how long that animation occurs. So it's half a second right now. But this is a cool thing, you know, again, because I'm modifying this file, like let's change this to 1.5. So it's going to animate for 1.5 seconds instead of a half of a second. I'll save the file. So I just pressed Control S to save the file. It just loaded it. And notice when I tap it, it's going to animate as a rainbow and fade out a little bit longer than it was before. So I just tapped it, and you can see that was a lot longer of an animation. So it takes it about a second and a half to animate. And it's built into the animation that it fades out. So over time, over that 1.5 seconds, it starts out full bright, and then it just fades out as it goes to 1.5 seconds here. So this is cool. This is how you can adjust the animation. I like, you know, value of 0.5 looks pretty good, but you can set this however you want. And then the frequency here, this is the speed of the animation. Basically, it's using a sine wave to compute that rainbow, and it moves it around all of the pixels. So the higher I set this value, the higher the frequency of the sine wave, the faster it moves around. So if I double this to 2.0, so you know, take a look now, that's a 1.0, frequency of once per second, it will do a revolution of the rainbow. I'm going to double this to 2, so this will be twice per second. So it's going to be twice as fast. So I'll save that, and it's actually going to run it in a second. So you can see now it's noticeably faster. You know, it's like you see that rainbow is happening twice as fast. And I can go quite a bit faster, like we can say, you know, maybe 15 times a second. So it's going to fly around now. Let's see what happens when I do that. So I set that, and yeah, you can see that is definitely some rainbow action there. And I can make it small, lower. So if I want to make it really slow, like, you know, maybe once every 2 seconds, I can set this to a frequency of 0.5. So I save that, and so now it's going to be really slow. So you can see it's a little bit slower. So it takes, you know, a second for this or 2 seconds for it to do a full revolution. So set this to whatever value you like. I think a value of 1 is kind of nice to start with, but it's kind of cool. You can play around with this and adjust the behavior of this. So those are basically all of the parameters for this. You can tweak these values and change the behavior of this. And it's really just as easy as editing the file. You know, here I'll just click save, and that's copying the updated source code onto the board, the main.py, and then with CircuitPython, when it sees a change to the file, it will go and run your main.py again automatically for you. So, you know, I don't have to have like a tool like Arduino or something to open and running my code. I'm just editing the code on my board directly, and it's updating it. It's changing how it works. So really cool what you can do here. You know, you don't have to be a big expert. As you know, it's maybe not as scary as Arduino sometimes to figure out, you know, how to get this tool to work and connect your board and all that stuff. You know, it's just a drive, it's just a file, edit it with whatever you like. So let's see, I'll dive in now to how this code works really quickly. So before I get too far into it, let's look at the app note for this accelerometer. And I've actually shown this off before with the digital fidget spinner project, and I'll put a link in the description when this goes up on YouTube. You can check that out. That's another project where I did an Arduino version and a CircuitPython version. It's a fidget spinner, which, you know, one of these fun little spinning things. But it's one that uses Circuit Playground, so that if you flick the board, it detects that flick using the accelerometer, and it spins around and animates the pixels. And I was using the accelerometer on Circuit Playground, the LIS3DH, really nice little low-cost accelerometer, to detect that flick. And I'm also using that accelerometer to detect your steps with the Circuit Walker sneakers here. And like I said, in the Arduino version, I did 2 videos on how I adapted this pretty sophisticated algorithm that does some filtering to the accelerometer data, and then it applies this adaptive step jerk detection, it calls it. Really cool thing where it at the end, when I kind of went with the final implementation of it that does all this advanced adaptive logic, it's pretty clever and pretty good at detecting a single step, like, you know, an up and down kind of movement of your foot. And it's good at detecting shallow steps and heavier steps. Now you might be wondering, okay, well, why can't I just take that Arduino code? In fact, if you're curious, if we go back to the Circuit Walker sneaker repository, you know, this Arduino Circuit Walker sketch, this is the Arduino version of it. So you might wonder naturally, okay, if I want to convert this to CircuitPython, why don't I just take this code and just convert the Arduino syntax into CircuitPython syntax or Python syntax? And you could do that, but you would run into some trouble because, like I said, and what I really wanted to show with a lot of these projects is that with Python running on a microcontroller, you have more constraints compared to Arduino. It's easier to write code because you're writing code in this nice high-level Python code. So if I'm looping through code, this is all Python code, I'm defining functions, it's all easy and simple to follow. But this code has to be interpreted. So there's code on your board that has to take that Python code and convert it into code that the microcontroller can actually run, because unfortunately the microcontrollers today can't directly run Python code, although maybe in the future they will. So that step of converting the Python code into code that runs on your microprocessor takes time, unfortunately. Like it has to happen on the chip that's built into this board. So it can only be really, as fast as the chip on your board. And the Circuit Playground board, the chip on here is pretty powerful. It's the SAMD21, but it's only running at a 48 megahertz. So compared to like your computer that's running at multiple gigahertz, it's much slower than like Python on your computer, but it's still pretty fast and impressive. So it's hard to do stuff in Arduino that does a lot of operations. Like if you're running a loop, if you're collecting accelerometer data 50 times a second, which is what the Arduino sketch is doing, and then you're filtering that data, so you're doing a bunch of math on that data. So you're running some square roots and some square operations, and you're concatenating these together and doing a bunch of multiplications. Trying to do that 50 times a second, you might run into some challenges. And in some earlier testing, I kind of saw what was like the fastest I could in CircuitPython read like the light sensor, for example, and I could only read it maybe 200 times a second, and that's just reading the sensor. That's not actually doing any math on that sensor value. And as soon as I start doing some operations on that, each of those operations has that overhead of having to convert the Python code into the microprocessor code. And so again, that just reduces what you can do. So I knew going into this, like looking at the Arduino version of this code, it's relatively advanced. Like a lot of that complexity is actually hidden from you. Oops, let me go back to, here's the Arduino version. I have this filter code inside of here. So this is doing a low pass filter on the accelerometer data, which is really just a bunch of multiplications right here. So it's basically just multiplying all these coefficients together. But basically for every accelerometer reading, it's going to do about 16 or so multiplications, and then it's got to do a square root, and it's got to do a bunch of operations. So all of that adds up to kind of tell me intuitively that I'm probably not going to be able to do that fast enough in CircuitPython, because not only do I need to do all those multiplications and operations, I also need to read my accelerometer data. So that's also some Python code that's going to need to run and get the accelerometer readings. And then I also need to light up the pixels. So, do like a frame of animation. And in that frame of animation, I'm doing things like using the sine function to compute a sine wave, and doing a lot of multiplications and things like that. So, it's not just maybe 20, maybe 24 or so multiplications to do that, filtering and math. It's all of that plus all of the operations to compute a frame of animation, plus all of the operations to read the accelerometer. So all of that, I kind of had this intuitive sense that I'm probably not going to be able to do that fast enough with the CircuitPython code. And there is a limit here to how fast I have to be able to do that in order for this to work, because this code, the Arduino version, it samples 50 times a second, and it applies this filter, this 3.66 hertz low pass filter. So, I'm expecting and that filter actually depends on the sample rate. So if I can't sample 50 times a second, I would actually have to change my filter and adjust its parameters to what my sample rate actually is. Like, let's say I can only sample maybe 10 times a second. So then I have to change my filter. My filter actually might get more complex because of that. But then the tricky thing is there's a limit to, if I sample 10 times a second, I can only filter and deal with a signal that's half that sample rate, so 5 times a second. So it effectively means like I can only deal with a signal that's, at most maybe, let's say if I'm sampling 10 times a second, 5 times a second. And so that just means the more time I have to spend doing that filtering and computations, that's the less time I have to grab samples. That's the, basically the slower my sampling gets. And once my sampling is, maybe let's say if I can't sample at least 6 times a second, then I'm not going to be able to detect like a 3 hertz signal And that's gonna kind of, just throw a wrench into everything, and that I'm not sampling fast enough, I'm not able to filter fast enough, and just everything kind of falls apart because of that. But that's if I try to exactly follow the Arduino version of this code. And, again, like I've shown with the fidget spinner project and everything else, you don't have to always follow that exact same idea, or, try and just port the code directly over. Sometimes your hardware has features built into it that make your life a little bit easier. And like I said, that the accelerometer, the LIS3DH, has this tap detection built into it. And with just like with the fidget spinner project, I can use the tap detection, and I can just change how I configure that tap detection so that it becomes sensitive enough to detect steps, but not so sensitive that it's just detecting random noise from, maybe just the shaking of, your body or your foot or something like that. So you can tweak this tap detection to get behavior that's similar to the Arduino sketch. It's maybe not as advanced, and it's not going to adapt itself to different steps, but it's still going to flash and light up as you take steps and as you touch the ground. So you'll still get a similar effect, and it's just going about it a different way. So we're going to use some features that are built into this accelerometer that I've actually used before. So it has this cool thing built into it. If I scroll down, it has this click and double click recognition. So this is the app note for the accelerometer that's built into this board. And this is not the datasheet. The datasheet actually has this info in here, but the app note is kind of nice in that the app note goes into a deeper, longer explanation. So I'll put a link in the description. You definitely want to check out this app note. But if I go to this click section, and I've actually talked through this before in the fidget spinner project, but basically I can tell this accelerometer that I want it to look for a spike of acceleration, so that rather than my CircuitPython code sampling the accelerometer as fast as it can, 50 times a second ideally, and then like looking for, does it cross this threshold value, I can let my accelerometer do that, and it can actually do that itself. And when it detects an acceleration that crosses a threshold, it can set a bit that my CircuitPython code will look for. So now my CircuitPython code just needs to look at my accelerometer and just say, hey, have you seen a spike of acceleration? And it just needs to ask my accelerometer that over and over. So rather than like trying to really quickly read the accelerometer and just look at each one of those 50 times a second accelerations and do all this math on it, I'll let my accelerometer do that. And then only when my accelerometer detects a step or a big impulse of acceleration will it tell my CircuitPython code. So that simplifies things a lot, because now my CircuitPython code only needs to run, maybe like twice a second at most, although it's going to run a lot faster than that, because as I'm taking a step, I'm only going to maybe take a step once a second, or maybe twice a second if I'm running or something like that. So I don't need to do as many operations. I just need to ask my accelerometer, have you seen a spike yet? Have you seen a click or a tap, is that what they call it? And when I do, then I fire off my animations here. So this click and double click recognition section goes into the details about how this works. And basically, I'm going to use the single click detection. And what you do is you set a threshold, like I was mentioning before. And then when it sees an acceleration on any of its axes, it has the X, Y, Z, the 3 axes. When it sees the acceleration go above that threshold, so this is the red line, imagine this is one of the axes, it goes above the threshold, and then it has to go back down below the threshold within this window of time. So when it sees something like this on the left-hand side, then the click detection says, that's a click, I've seen a single click, and it can notify your Python code. And there are a couple ways it can do it, but I'll show you how I did it in the sketch here. But that's basically a way to detect a strong spike of acceleration. And it's interesting in that, that time window, it basically, that spike has to happen within that window of time. And so they show here, if you see a big spike of acceleration, but if it stays up at that high level of acceleration past your window of time, then it won't consider that a click. And so this is actually kind of like a high pass filter in some ways, where this is looking for high frequency noise, like something that happens within a short period of time. Like I see a spike of acceleration that goes up and down within a little window of time, because if this window of time is really large, I can see like a short spike of acceleration, but if I see a really long spike of acceleration, it's going to fall outside of that window, and I won't consider that a click or a tap. So it's kind of interesting how to think about this. So it's kind of like a high pass filter in some ways. So that's effectively what those two little configuration values that I had at the top here are configuring. So I'm configuring that threshold in gravities and the time limit, that window of time that it's using for that click detection. And so that's the threshold value right here and the time limit value right here. Now it's interesting though, because the way you configure this accelerometer, you don't actually tell it like this is my threshold in gravities. So if you go through and if you read this click and double click detection section, it talks about the registers on this accelerometer which control this click detection behavior and the actual values that you set inside of here. So this click threshold register, you set it to a 7-bit value, an unsigned integer, and it actually that will then map to your that gravity value threshold, but it depends on the range of values that you set ahead of time. So with this accelerometer, it has different levels of sensitivity. So it can detect like plus or minus 2 gravities of acceleration. So you get a small range of acceleration, but you have a lot of accuracy or a lot of precision within that range. But you can increase that. You can say, I want a wide range of acceleration, like up to plus or minus 16 Gs, 16 gravities of acceleration, like a really strong force. But you get less precision within that range because there's just a certain number of bits that this thing can detect for acceleration values. So let's say it's like 10 bits of data. So if you have 10 bits of data spread across 16 gravities of range, you have less values that you can, your range is really large, but you can't tell the difference between like a very small change in acceleration. Whereas if you set that window to a really small value, like plus or minus 2 gravities of acceleration, you have that same 10 bits of data, but within a smaller range. So now I can tell the difference between a small change in acceleration. And so in this sneaker sketch, so if I scroll down a little bit, I'll show you where I start configuring the accelerometer. So if you scroll down past the top of the code, so the configuration we've already talked through, I have some helper functions that I'll come back to in a second. There's actually some gamma correction stuff that I do that I'll talk about in a second also. But if I scroll down to this initialization code that kind of happens on startup, first I just initialize the neopixels and I turn them off. And then right here, I actually initialize the accelerometer. And I mentioned like this is specific to Circuit Playground Express. So there's a certain I2C address that you need to set and a certain I2C bus that you need to set for this. But basically this is just the initialization in CircuitPython of how you create an I2C bus. And then I'm importing, or I'm using the LIS3DH accelerometer library. This was provided in that bundle that I copied over ahead of time. So I'm creating an LIS3DH object using that I2C instance. And then right here is where I set the range and the data rate of the accelerometer. So I'm setting the range to 4G. So this means that the accelerometer can detect up to plus or minus 4G of acceleration on any of the axes. And so that's important because that controls that threshold value right here. So if I have plus or minus 4Gs of acceleration, then 1 bit inside of this threshold value maps to that 4G divided by 128. So this is kind of how I convert from a value in gravities, up in my configuration right here, you just tell me I want that threshold set to 1.2 gravities. But then to actually configure my accelerometer, I need to do some math to figure out, based on the data range, what's the threshold value I should set that gets me to a value of 1.2 gravities. And so I actually do that in the startup of the sketch. So right here, after I set the range and the data rate, I compute what is my tap threshold value. And so that's basically taking the tap threshold that I set in gravities at the top of the sketch. That's a value of like 1.5 or 1.2 or whatever you want to set. And then I'm dividing that by 4 divided by 128. And so that 4 divided by 128 is coming from this equation right here, where basically the datasheet or the application note's telling me for the threshold register, 1 bit inside of this 7-bit value represents your scale, your plus minus 4G divided by 128. So it's just basically, you're taking a fraction of your range, and then you're using that to set your threshold value. And that's actually what you see. So if I connect to the serial terminal on my board, and if I just press Control D to reset my board, I actually print out, oops, let me press Control C actually to stop, and then there we go, now it's running again. So you can see it's actually printing out using tap threshold value 39. So if I go back to my code, I compute my tap threshold value, and I actually do a quick check because I might set that value too high that I can't represent it. There's a limit to how high of a threshold I can set. And if I set it too high, then I'll actually flash an error message. I'll show you in a second that. But I also just print out what is the tap threshold that I've computed ahead of time. So in this case, it computed 39 as my tap threshold. But let's try changing that threshold value at the top here. So let's change this to a value of, let's say 1.5. So we'll go back to the value it starts with. I'm going to save this. So I'll just go to File Save, or I can press Control S or whatever. And then I save this, and I'll go back to here. And it just reran my code because it noticed I saved the file. And now notice it changed that tap threshold value to a value 48. And so it's just doing the math that the datasheet tells me here. It's doing the math to convert from a value in gravities to a threshold register value, which depends on the data rate that I calculated ahead of time. So this is kind of nice, and that this makes it easier for me as a user, in that I don't need to know, like, oh, I need some magic 40 value or 48 value. Like, what does that thing even mean? I want a value of 1.5 Gs here, and I'll just have my Python code compute that. And so that's kind of the power and the flexibility of Python, because this only happens once at startup. So I don't really care that I'm doing some of this math. Like, sure, it's going to take a little bit of time, but this is happening once at startup. It doesn't happen every loop iteration, so I don't really care how long this takes. So that's what's happening right here. But like I said, there's a limit. So in the application node, in the datasheet, you only have 7 bits to represent this click threshold. So that means at most you can set a value between 0 and 127. You can't set anything higher than that, because that's the highest value that a 7-bit number can represent. So what happens if I try to set a really high gravity value? Like, let's say I want to set 15 Gs. So you've got to like launch your shoe off of your foot like a rocket to detect this tap detection. So let's do that. I'll save this file, and let's see what happens here. So I just saved it, and notice this is flashing now. So it's actually flashing in SOS. You can see it's flashing 3 times fast red and then 3 times slow red. And it's actually telling me your tap threshold is too high to represent. And so that's just because in the code, I'm figuring out, did you tell me a threshold that's too large? Based on the range of accelerometer values that the accelerometer is using, there's a limit to how high that threshold can be set. And so if I've exceeded that limit, then it catches that and warns me as a user and says, oh, okay, you can't set that value. You have to lower this. The hardware doesn't support that. So if you play with the values and you see the board flashing like this, you can open the serial terminal. You can kind of see this is the error message that it's telling me. So I need to go and decrease this value to something smaller. So I could probably set this to a value like 2, for example. So I'll save that, and then we'll see. So yeah, that gives me a value of 64. Let's see, if I double this to 4, that's going to start getting close to 128. Let's see if that's, yep, that's too high. So it looks like 4 is a little bit too high, but I can probably do like 3.5. Let's see if that works. So if I do 3.5, then yeah, that gets me within the range. That's setting a tap threshold of 112, so I'm pretty close to 127, but not over it. So that's enough to run. So that just means that I have to exceed 3.5 Gs of acceleration in order for it to fire off the tap detection. Now, if I tap it with my finger, I can probably do that. Yeah, I have to give it kind of a strong tap. But with my if I'm moving the shoe, notice I can kick this thing quite a bit, and it's not doing anything. Like, I can even tap it against the ground. So you can see increasing this decreases the sensitivity, which is why you want a value that's probably close to like 1.5 or so. So that's the tap threshold. And I do the exact same thing for that time window. So you can see here's where I do that check for the tap threshold. Here's the exact same thing where I do for the time limit. So if you go back to the application note, that threshold, there's another register called time limit that's like the threshold. And just like the threshold, the value that it's set, it's not an absolute value in seconds. It's actually a value that depends on the sample rate of the accelerometer. And so again, in the setup right here, I can tell the accelerometer what sample rate I want. And it's kind of nice. It has a 50 Hertz sample rate, which is the sample rate that I was using in the Arduino version of this sketch. So I can tell the accelerometer, hey, sample yourself 50 times a second. And that's nice in that my Python code does not need to run 50 times a second now. It's only the accelerometer that's going to run 50 times a second. So it's cool that my Python code can be a lot slower. I don't need to worry about that. The accelerometer is going to be sampling itself 50 times a second. And then that time limit is set based on this data rate value. And so it mentions, here's the equation for it. This ODR value is kind of your data rate in hertz. So my ODR with a data rate of 50 hertz, my ODR value is 50. So it's 50 times a second. So 1 bit inside of this time limit value represents 1 over my 50 hertz sample rate, or like a 50th of a second effectively. So with that, I can calculate, just like I calculated the threshold value, I can calculate, given a time window in seconds. So up at the top, here's my time window. I want a quarter of a second. I can calculate, okay, what is my time limit register value that I need? Or how many of those 1/50th of a second ODR cycles should it see within that window of time? So it's doing that calculation for you. And again, there's a limit because this is a 7-bit value in the datasheet they mention. I can only go up to 127 for this value. So if I try to set this time window to be too big, like let's set this to like 50 seconds, let's say. This is probably gonna be way too big. So I set that, and now it's warning me, hey, I get that same little SOS, and it's telling me your time limit is too high to represent. So I'm gonna need to decrease that time limit. And I'm not sure what the highest value is that I can set. Like, what if I try and set 5 seconds? Let's see how that gets me. Okay, yeah, that's a little too high to represent. So let's try like 2 seconds and see if that's representable. Okay, so 2 seconds works. So you can see, and just like with the tap threshold, I print out what's the time limit register value, or that raw value that I'm computing. So this calculated a value of 100. So given a 2-second window of time, it's going to calculate a value of 100 that it needs to set inside of this time limit register. So you can see how it does that down in the code right here. So that's where it does that calculation. And so this is neat. So this just changed that window of time. So since I increased the window of time to 2 seconds, that just means if it sees a spike of acceleration up and down within a 2-second window of time, then it will consider that a step. So this basically just means I need to see that kind of 1.5 G kick of acceleration within a 2-second window. That's a pretty big window of acceleration. So that's fine. I can use a 2-second value, but I think I was playing around a little bit, and this doesn't really change the behavior that much, but something around a quarter of a second seems to make sense for at least taking kind of steps. Because if I set this so high, it only takes me maybe a second or so to take a step, and so I might get like multiple steps all within one window of time, and this kind of slows down the behavior of this a little bit. So I want this to be a low value, but like I said, not so low. Like if I set this to like a 1/10 of a second, let's save that and see what happens. So this computed a time limit value of 1. So this is like the lowest value it can represent. And it actually might be a window of time that's larger than a 1/10 of a second. So I'm picking the smallest window of time that can represent at least the value that I want right here. So this is using kind of the lowest value. And this just kind of means it needs to see a really fast, sharp, if I tap this, I can give it a quick little, oops, I just reset my board on accident there. So that just kicked me out of my my window. Let me reconnect to the serial terminal here. Oops. It's TTY. I pressed the reset button as I was meaning to reset the board. Oops. Let me make sure that I get the baud rate correct. There we go. So let me just make sure I'm at the Python prompt. There we go. Okay, sorry. So when you're tapping the board, don't tap the reset button. Anyways, though, so if I tap the board, that gives it a quick, sharp spike of acceleration. But if I'm kicking it with my foot like this, or, as if I'm taking a step, it has to be a really fast step, a really fast kick of acceleration. You can see like it's hard for me to get it to detect that. Like sometimes I can do it, but sometimes I can't. So again, that's just how that time limit changes the behavior here, and why a value of a quarter of a second seems to make the most sense for this. So that's all that I use with the accelerometer. I'm using the tap detection and then tweaking the time limit and the threshold values so that I can adjust those. And then rather than like making you, the user, set these real low-level kind of register values where you have to intuitively know like what is the data rate and the range. Nice thing is I'll just calculate that. It's I can write the Python code so that now you as the user can just provide nice high-level values like I want this threshold in gravities and this time window in seconds, and then I'll calculate those register values and set them appropriately. So if we go back to that setup code, so again, I set the range and the data rate to some kind of default values that I like the 4G range and a data rate of 50 times a second, and then I calculate that tap threshold and time limit. And then the last thing is to actually put the accelerometer into the tap detection mode. In the LIS3DH library, we have the set click function, which turns on the click detection. I'm telling it that I want single click detection, so 1, a value here, and then I give it that tap threshold, and I can also tell it the time limit value that I want. By default, it uses a value of 10, not 10 seconds, but actually a value of 10 that it computes. Not necessarily that it computes, but it's just using a 10 value, which is going to change based on your data rate. So I don't want that default value though, because I've calculated the value that I want ahead of time right here. So luckily in the library we provide optional parameters where I can override the time limit value. So this is where I set that explicit time limit that I calculated ahead of time right here. So this turns on the click detection, and at this point I'm ready to go into my main loop. And so like I said, the main loop is now effectively, instead of having to sample the accelerometer as fast as it can and do all that filtering and all that magic, I just need to look for, has the accelerometer seen a click event yet? And it's actually down at the bottom of this main loop that I do that. So right here is where I detect, if I call this lis3dh.read click function, it returns 2 Boolean values. It returns a Boolean that says it's true if it's seen a single click, and a second Boolean that's true if it's seen a double click. So that's the second parameter here. Now, I don't care about double clicks, but this function always returns 2 Booleans, so I need to tell Python that I expect those 2 values to come back. But if that single click is true, then I've detected a step effectively. I've seen a big impulse of acceleration that went above and below the threshold within that window of time. And so now I should animate my pixels. And the way that I drive the animation is basically I have this pixel animate variable, and this is the amount of time that's left for the pixels to animate. So, I tap these and you can see they animate, they do a little rainbow cycle and they fade out. So when I detect a step, I set this pixels animate to the amount of seconds that I want this pixel animation to run for. And so you can see here's where I just set it to this value that I set in the configuration ahead of time. So way at the top, the step flash seconds is 0.5, so half of a second. So when I detect a step from the tap detection, I say, okay, animate for the next half a second, or whatever this step flash second value is. So it's going to set that. And then at the start of the loop, I basically figure out how much time elapsed since the last loop iteration. So I keep track of when was my last loop iteration, and I use the time.monotonic function. That's the function in CircuitPython. It's basically, it's kind of like a clock. It's not the wall time. It's not going to tell me the time, like, it's 2:35 right now. It's just going to tell me a value that increases at the same speed of a wall clock. So, every time a second elapses, this time.monotonic value will increase by 1. But it's a floating point value. You actually get millisecond accuracy with this. So I can get, nice floating point values. But this is effectively my clock. I don't really care that it's 6 p.m. or whatever. I just care that it's been a tenth of a second since the last loop iteration, because I need to know how much time elapsed since my last loop iteration. Because what I do is I decrement this pixel animate variable. So that tells me how much time is left in my animation. I saw my last loop iteration took maybe a tenth of a second or whatever. So I'll decrease the amount of time left. With this line right here, I want to make sure that doesn't go below 0, because I don't have a concept of less than 0 time left. There's all that. That's just a positive value. I never expect the negative time value. So I'm using the max function, basically say, take my pixel animate, subtract the amount of time that elapsed from my last loop iteration, and then pick the largest value between this and 0. So if I suddenly get to the end and my pixel animate minus the time it took for my last loop iteration, if this becomes negative, it's actually going to be less than 0, and the max operation here is going to pick 0. So this is going to ensure that my pixel animate value never goes below 0. So it's just a nice little shorthand way of doing that. I could do an if statement if I wanted that says, if pixel animate is less than 0, set it equal to 0. But this is nice that it's a little one-liner effective. I just use the max function to say, I want to make sure that this value is never less than 0. But if it's greater than 0, then it's going to pick this side of the max function, this pixel animate minus delta here. So this is just how I can make sure that my pixel animate value over time will decrease until it gets to 0 and then it stops. Now then I check if there's still time left to animate the pixels, do that pixel animation. So that's what this little block of code does right here. And I'll come back to this in a second. If there's not any time left, so if my pixel animate is 0, so if this if clause fails, then it's just going to clear all the pixels. So it's going to call pixels.fill with a value of 0, 0, 0. That just turns all the pixels off. So this is basically after half a second has elapsed from a step, then that pixels animate has gone all the way down to 0, and now this part of the code is going to run. So it's going to turn off all the pixels. But if I still have time, so if that pixel animate is positive, I'm going to animate the pixels. And so I call this Animate Rainbow function, which is a function that I defined ahead of time up here. So Animate Rainbow, this does a single frame of the rainbow animation that you see right here. And what it does, I won't get too far into this. I've actually done this in a lot of the projects, and I talked about this in the Arduino version. This code is effectively the same as the Arduino code. This is just converted over from Arduino into Python syntax. But I go through all 10 of the pixels on the board, and I basically calculate using the sine function. The sine function is going to give me a value that oscillates from -1 to +1, and I use that to map the value to a color hue. So instead of using the red, green, blue color space, I use the hue saturation value, or HSV color space. Because it's kind of nice in that with the HSV color space, if I want to change the color from any of the rainbow colors you see right here, that's just a different hue value. The hue goes from 0 to 360. It's a value in degrees. So 0 is red, 60 is around, I think, a yellow color. You can look this up on Wikipedia. I think 120 is like a greenish color, all the way back to 360 where you come back to red. So you basically do the whole rainbow across 360 degrees. And it's kind of nice in that this just means the way I can animate this, this rainbow, I just need to get a value that changes over time, this sine wave that just smoothly changes from like -1 to 1. Map that to a value then that smoothly changes from 0 to 360. So that will change my hue in a nice kind of smooth sine wave pattern. And then I'll use that HSV color space. I can convert HSV to red, green, blue color, because red, green, blue color is the color that the NeoPixels expect. And so that's where this function right here, this HSV to RGB function is called. And that's this function right here. And this is actually, I've taken this directly from Arduino, which actually the Arduino sketch used a version from this page online that I referenced in the Arduino sketch, which actually I should probably put inside of the CircuitPython sketch while I'm thinking about it. But if I go back here, you can actually see there's, from this web page, there's just a standard formula this is running through. But this is a good example of converting Arduino code into Python code. So the code, it's similar, but it's a little bit different in that it's kind of nice. I don't need to declare the types of variables, but I do still need to think about the types because, oh, it's actually kind of funny. I just noticed I have a semicolon here, which that's not technically Python syntax. So it's funny that it must be ignoring that. But that's one difference, obviously, is the syntax is different. So in the in the C++ Arduino style code, the syntax is different. You've got semicolons, you've got curly braces, all kinds of stuff like that. Whereas in the Python code, it's a little bit simpler. I don't need that stuff. But you do have to be careful. So some of the gotchas in Python, by default, division is floating point. Whereas in C and C++ in Arduino, division depends on the type of the two operands. If you have two integers and you do division, you'll get integer division. But in Python, even if you have two integers, in Python 3 specifically, and in MicroPython and CircuitPython, no matter what, you will get floating point division, which may or may not be what you want. Now, it just so turns out this code wants floating point division, so I don't need to do anything fancy. But just be aware when you're converting code over, it's not sometimes a one-to-one change, especially when there's math operations. You need to kind of look at what are the types of my variables, what are the operations being performed, is there division, is there multiplication, and do I expect this to happen with integers or floating point values for this. But basically, I've just converted the syntax, and you'll also notice, like in Python, there's no switch statement. You don't have that concept. You can do if statements with a bunch of else if clauses. So that's what I've done right here. Whereas in the Arduino version code, it's using a switch statement. So kind of interesting. You can just see different ways of doing logic like this. But that's ultimately what this HSV to RGB function does. I also added into it, it does gamma correction, which I talked about this in the Arduino version of this in the previous two videos. This just makes it so that the colors are accurate, because your eyes actually perceive color at in a nonlinear way, so that, you know, with a NeoPixel, a brightness of 255 is exactly twice as bright as 128. But it turns out your eyes don't actually perceive that as twice as bright, and it even changes depending on the color. You have like, I think more or less blue receptors. So you see, or sorry, you have more blue receptors. That's why blue LEDs on electronics are so bright, because you see more blue light in your eyes. So this gamma correction tries to correct for that nonlinearity, and it does a lookup in a table that I created ahead of time. So there's this magic table here. You can go to this guide that I referenced in the comment. This explains a little more detail of what's actually happening here and how these were computed. But this just makes the colors look more accurate, so that when you see that rainbow, it actually looks like a rainbow of colors. If you don't do this gamma correction, your colors get washed out. They look brighter than they actually are, because just the math is, you know, maybe computing values that are exactly half as bright, but your eyes don't see things exactly half as bright as that. And so that's what the gamma correction does. And it's nice I can do that automatically in this HSV to RGB function, so that it'll just happen for me, and I don't have to do that as an explicit step. But that's what the Animate Rainbow function is doing. Is it's basically going through each of the pixels. It's using a sine wave to just calculate, okay, what is the color of each pixel? It offsets the phase of the sine wave depending on the pixel position. So like, you know, pixel 0 is a different position from pixel 1 and 2 and 3. And they're 10 pixels. So as the pixel position changes, the phase of that sine wave will also change, which just changes what color the sine wave starts with. And that's why you see the rainbow move around instead of all of the pixels lighting up the same color and fading away at the same rainbow color. You see it as if the rainbow kind of moves around because the phase of each of the pixels is different, and the phase depends on the position of the pixels for that. And so it's just, again, just comes down to the sine wave equation and how it works. And then I'm using Lerp, the linear interpolation function, which I defined up here. I use this a million times. This is just a way to convert a value from one range. Like my sine wave gives me a value that ranges from -1 to 1. It's going to give me a value that's within, that's proportional to that -1 to 1 range, but within a new range. So that range is 0 to 360, because my HSV to RGB function expects the hue to be a color, a value in degrees that range from 0 to 360. So this Lerp function is just doing that conversion to say, my sine wave gives me a value that goes from -1 to +1, but I really want a wave that goes from 0 to 360. So I'm just converting from -1, 1 to 0 to 360 range. And so that's what that linear interpolation does right here. And so that's what I'm doing. I'm just computing the sine wave color of each of the pixels. I compute the hue for my HSV color space. The saturation I just always set to a value of 1. That's full saturation in the HSV color space. Basically, the lower your saturation, the closer to white your pixels are. And then V, the value, the value, the closer to 1, the more accurate your color is. Like, you get the strongest intensity of color, and the lower your value, the darker your color is. So a value of 0 is actually off. There's no color at all. Even if your hue is, you know, like, let's say a value of like 120, which is like a green hue. If I have a value, a V value of 0, I'm going to get a black pixel, because that's just the way HSV color space works. You know, the hue kind of tells you what color you want, but then those S and V parameters tell you the intensity of the color or the brightness of the color. But this is kind of nice, because this gives me a way to fade out the color of the pixels. So you can see, you know, I tap these, and over that animation time window, they fade back down to black. And that's because I take as a parameter to my Animate Rainbow function this remaining parameter. And if I pass in a value that goes from 0 to 1, I'll use that as my V value. And so if I send in a value of 1, I get full bright. And so that's like, as soon as I tap this, you see that bright initial blast of color. So that's a value of 1.0. And then over time, if I go back into my main loop here, I actually calculate that remaining value before I call Animate Rainbow. And I calculate it as a fraction, how much of that window of time for my animation, that half-second window, how much of that has elapsed. So if I'm just at the start, and almost no time has elapsed, if I have, about a half-second left, then I'm going to get a value of 1. Let's say in the previous loop iteration, I detected a click, so I set pixel animate equal to this step flash, like half a second, 0.5. And now I get in my next loop iteration, this is still set to 0.5, so it's set to step flash, and if I divide that by step flash, I'm going to get a value of 1. So that's going to give me, my maximum value, my maximum amount of time is left, my 1.0 value. And the nice thing is, I can just set that directly as the HSV, the V value of my color directly. So, at the start of my animation, I get a remaining time of 1, and then over time, it's gonna decrease. So, after maybe a quarter of a second has elapsed, then my pixel animate is going to be set to 0.25, and 0.25 divided by my step flash, which is 0.5, 0.25 divided by 0.5 is going to give me a remaining value of 0.5, like half. So I'm only seeing half of that, or half of my time has elapsed, basically, or half of my time is remaining. That's going to get passed into my Animate Rainbow function, which is going to get passed in as the HSV, the value of my color. And so that's how my colors fade out over time, because this remaining value goes from 1 down to 0. So it starts out at 1 at the very start of my animation, and then after a half second has elapsed, it gets down to 0. And so that's why it kind of smoothly fades away over time like that. It's kind of nice how by using that HSV color space, I effectively get for free some of these neat little effects like that. I don't have to have all this logic in my animation that says like, okay, some number of time has elapsed, now decrease the brightness of my pixels. Because the color space I'm using intuitively has a notion of brightness, I can just animate that. I can just change that remaining value over time, and it will effectively animate the brightness of those pixels over time. So that's really it to the main loop for this. Like, I just have this main loop. It calculates how much time elapsed. It drives the animation. It updates the pixels right here, and then it checks to see if the accelerometer has detected a click. And ahead of time, it set the tap threshold and time limit values to kind of the values that the user wanted based on what it computed. And then it's just waiting in this loop to see, once the accelerometer tells me that it's detected that big spike of acceleration within the window of time, that I should do some animations here. I should set a timer and just animate for that period of time. So that's all that there is to this sketch. It's pretty similar to the Arduino version in the sense of it's doing the same basic things. It's just, instead of processing the accelerometer data in the Python code, I'm letting the accelerometer do some of its processing. And it's not as fancy as the Arduino code. Again, the Arduino code does this low pass filtering, it does this adaptive jerk step detection, all of this kind of cool stuff. Because it runs really fast. The code is more complex, unfortunately, because of that. Whereas in this Python code, it's not as fancy as the Arduino version, but it's still pretty good, and it still detects, when I take a strong step here, or when I tap it on the floor like that, it picks that up, and it's able to detect that movement as a jerk and acceleration for this. So I think this is pretty cool. And again, it's just showing when you're going from Arduino to CircuitPython or MicroPython, you need to look at what your code is doing and understand what might not be as fast in CircuitPython. Like you could actually try, you could just directly convert your Arduino code into Python code and try things out, but you'll probably run into issues sometimes where maybe things aren't fast enough. And so then you need to kind of think about, okay, are there other ways that I might approach this problem, or other ways to detect this? And I think I got a pretty good solution here though with this CircuitPython version. So I'm using the tap detection to look for kind of a strong peak of acceleration. And it works pretty well when I put this on my feet and walk around. Every time I'm taking a step, it's lighting up and animating. Then when I stop, it's not animating. If I just make a small little movement, it won't pick that up. It's only when I really I pick up my foot, when I exceed that 1.5 G of acceleration, does it pick that up as a step that was detected. So okay, so if folks have questions, throw them in the chat. I think I'll wrap up this stream since it's starting to get a little bit past an hour. And I'll see if I can answer them. Let's see. Someone's mentioning, oh, let's see, let me go back to the main view real fast also. Jump back there. Let's see, so someone is running this. Cool, excellent. I'm glad that you're running this on your board. So let's see, this could be the target for scoring a game when you throw rocks at soda cans balanced on a fence post. Yeah, that's a good idea. So someone is suggesting, like, you could put a Circuit Playground board, maybe on like, I don't know, set up some milk cans, for example, or I don't know, you could just put this on a wall, really. Put this on a wall or on the floor or something, and then, yeah, you have to throw something against the wall, hopefully not breakable, be careful. Throw like a beanbag or something against the wall, and it has to hit the wall with enough force that it shakes the accelerometer enough to detect that change and then lights up or something. That'd be kind of cool. I remember in college, a lot of people would sometimes play this game called Cornhole, where it's like you have a little a board on the ground with a hole in the middle, and you're supposed to throw a beanbag into it. It's kind of like horseshoes, but I don't know, a little bit different. And so you could maybe do that. You put your Circuit Playground on the board and then it on the ground, and then when something hits that board, that's going to vibrate a little bit. And if you tweak those thresholds enough, that they can pick up that vibration, but not just like maybe random noise of people walking around and stuff near it. You could probably do that. You could do like make a game out of it. It'd be kind of cool for that. So let's see. Someone mentioned too, put on the back of a motorcycle. To warn people that the road is too bumpy. Yeah, that's a good point too. So again, this accelerometer, it detects forces, and so moving something causes a force to be applied to it. And I have kind of wondered, it would be kind of fun to do a project that's like, you drive around and detect how unmaintained your roads are, like how many potholes are on your road, just based on how much your board is shaking because you're driving around. And maybe you could send a report to your city to say, hey, this road is pretty bad. This road is worse than this one. Maybe you should fix that one. So that'd be a fun one. Let's see. So some folks enjoy this stream. So yeah, thanks for letting me know. Oh, and someone was wondering where you can get these shoes. Yeah, these are the circuit board Chuck Taylor shoes. You can't get these anymore, unfortunately. So it was like maybe 3-4 years ago, Converse made this run of these shoes. I got mine on eBay. So check eBay, search for circuit board Chuck Taylor or circuit board Converse, and you might be able to find some of these still around for that. Maybe if we all ask Converse, maybe they'll bring back that pattern and bring back the circuit board shoes. So that's where I got those. Okay, it looks like that's it as far as the questions go. So I'll wrap up the stream. So thanks a lot for watching. This was part 3, the thrilling conclusion to the Circuit Walker Sneaker project. So like I said, this is the third part. The first 2 parts, I looked at an Arduino version of this and went into some pretty sophisticated filtering and algorithms to detect steps and try to be really accurate about it, where I took this adaptive step detection algorithm and converted it into Arduino code and got it to run on Circuit Playground. And then in this video, in this third part, I wanted to do the same, but using CircuitPython and Circuit Playground Express, because I really want to kind of show, here's Arduino versions, and then here's a CircuitPython version of this project. And so I saw the big point of this video is that for the CircuitPython version, I can't be as advanced as the Arduino version because I just don't have the processing power, at least on this board, to do all of that math and all of that fast sampling. Because this is interpreted code, so there's a lot of overhead to do that. It's nice in that my code is a lot simpler and easy to understand, because if I look, let's see, there are 240 lines of code in the Python version, and in the Arduino version, there's 300 in the sketch, and then another 50 in the filter. So there's 350 lines of code in the Arduino version versus 250 in the Python version. So that's quite a difference in code. And so just the complexity is different here. So it's trade-offs. Nothing's perfect right now. I'm sure in the future we'll probably have more powerful boards where, potentially we can probably start doing some of that math and filtering in Python. And so that'll be kind of cool. So maybe in the future I'll be able to revisit this project when we have some fancier boards. But until then, I think this is a good kind of workaround, is just using some of the features built into the hardware. The accelerometer has this tap detection that can itself look for strong spikes of acceleration, and so we can get some basic rough tap detection using that logic. So that's it. So I'll wrap up this stream. So thanks a lot for watching. This is Tony from Adafruit. Check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos. Check out twitch.tv/Adafruit. That's where I like to stream this video. Usually every Friday I do a project or a video. So definitely stay tuned, check out those channels, and we will have all kinds of fun content. Click the like or the comment or the subscribe. Let us know that this is cool stuff, and we will keep doing fun content like this. So Until next time, this is Tony from Adafruit. Thanks a lot for watching. I'll see you later. Bye.